Okay, today we started to talk about how flow and objects interact, and specifically the forces that they exert. The problem that we're going to be setting up for the next week or so is a case where we have uniform flow encountering an object of arbitrary shape. We'll simplify that in various cases as we go along. The force that the fluid exerts on the object in the direction of the flow is called the drag force, F sub d. And then the two components of the force that are normal to the direction of the flow are the lift forces. Lift force traditionally is, of course, in the vertical direction, but you can also have a lateral lift. The key thing is that it's across the flow direction. Now, the way we can think about the total force that the fluid is exerting on the object is to consider a little area element, like the one I'm coloring in red here, and then the forces that are exerted on that. So we have the pressure, force, normal force per area, and the shear stress, shear force per area. The angle that the pressure force makes with the flow direction, if we define that to be theta, then the total drag force is just the area integral over the entire surface of our object of p cosine theta dA, and then the integration of tau sine theta dA. The lift force, we just have to take the other components of those area elements. It ends up being a minus sign area integral of p sine theta dA, and again the double integral of tau, this time cosine theta dA. So really our mission now for the rest of this next week and a half is to understand how pressure and shear stress vary along the surface of objects that are interacting with fluid. The first case that we started talking about today was the flat plate and the boundary layer that develops on the flat plate. So if we consider a long flat plate, here's a solid plate, again approach velocity u0, the sketch that I wanted to set up for the boundary layer that develops is a region adjacent to the plate that experiences the frictional effects of the plate. That's going to be our boundary layer. The boundary layer is described by boundary layer height, delta of x. We talked about three different ways of calculating that boundary layer height today. Outside the boundary layer, the velocity is the free stream velocity, or u0, and it's uniform. Within the boundary layer, we have a gradient that transitions from u0 to the no-slip condition. So as we move along our boundary layer, the thickness of the boundary layer grows through the viscous momentum transfer away from the plate, which means the boundary layer gets thicker. So delta is increasing, from which we can estimate that the shear stress has to decrease. The way we can think about that is the gradient across the boundary layer is decreasing because du dz, now where do I write this? So tau is equal to mu du dz, which means tau is approximately mu u0 over delta. So as delta grows, tau decreases. The last thing that I'll mention, I'll just kind of fit it in the corner here, is the implications for the development with x, where x is the distance from the leading edge of the plate, drawing it down here by the plate again, so that the boundary layer increases with distance, there's delta of x, and the shear stress decreases with distance, there's tau of x. Next lectures we're going to talk about the actual variation of tau. We're going to integrate that to define the drag force. And then from there we'll move on to think about more general drag forces that don't involve just this viscous boundary layer.